Okay, so the first speaker this afternoon is Brandon Creutz from Canterbury University, who will speak about descent obstruction on constant curves over global function fields.
Well, thank you for the introduction and the invitation to speak here. So everything that I am going to talk about today is joint work with Felipe Voloch. So what I want to consider is C over K. So this is a smooth, projective, or we'll say smooth, proper, and geometrically connected curve over a global field. Okay, so that's what I'm looking at. And I want to make two assumptions that I'm going to have sort of in place throughout the talk. So the first is I want that the Tate-Shafarevich group of the Jacobian of this curve is finite. So J is the Jacobian of C. And well, we expect this is always true. We certainly don't know how to prove that, but we do know how to prove it in some cases. And in particular, in the cases that I'm quite interested in, which were the constant curves over global function fields, the Jacobian is a constant variety over a global function field. And it is actually a theorem of Tate and Milne that the Tate-Shafarevich group is finite. So it's sort of an innocuous assumption in that context. But just sort of to simplify some of the exposition, I'd like to assume it throughout.
So what magic word did you use about it?
Sorry? Well, I'll come to that later. I said constant, so meaning that it's defined over a finite field, and we consider it over a global function field, but it's defined over the finite field. Yeah. So we'll come there, but for now I'm just sort of working in this generality. And the second assumption that I want is that we can embed the curve in the Jacobian over K. All right. Now, certainly this is also not always true. But just to simplify things, I'm going to assume that we have that, or sort of, I don't want to fix the embedding necessarily, but I want to know that there is one, which is equivalent to saying that there's a zero cycle of degree 1 on my curve. And again, in the context which I'm going to be talking about for these constant varieties, this is always true, basically by the Weyl bounds in this case. Okay, so those are the two assumptions that I want to have in place. And then what do we want to do? Well, I want to look at the rational points on this curve. Okay, and so I want to sort of recall an idea that goes back to Shirashkin, which is about 20 years ago, for how you do this. So, I mean, okay, so maybe the first part of the idea goes back a lot further, maybe to Mordell or even before that, but we can embed the curve in the Jacobian. So certainly we can view this set of rational points on this as a subset of the set of rational points on the Jacobian. Okay? And thanks to this assumption here, if this is verified, then at least in principle, this is something that we could compute. And by compute it, I mean you could compute generators for this finitely generated abelian group. And well, then the goal would be to sort of decide, you know, where does this sit inside there? If this group, for example, is finite, you just take the finitely many points and check if they lie on the curve, and you're done. Okay? If it's finitely generated, you can't really do that. So you have to work a little bit harder. So what Shirashkin considered was, well, we look at what happens at the level of adelic points. So you embed the rational points on the curve into the set of adelic points. You can do the same thing for the Jacobian. And then you have a commutative diagram like this. And the idea is, it's one that comes up in a lot of contexts, you're trying to find this. Well, this has to lie in the intersection of these two images. Right? So you look at the intersection of the adelic points on the curve with the set of rational points on the Jacobian. And well, if you do this, you're not actually yet really doing much, because what is this? This consists of adelic points on the curve, which are global. This is exactly the set of rational points. Okay? And so you can't really get your hands on this. What he considered instead was something that's slightly larger, but perhaps something that is sort of more amenable to saying something concrete about, which is to take the topological closure of this set inside the adel. So this is the closure of that in there. And what he showed was that this is actually equal to the set of adelic points on the curve, which are orthogonal to the Brauer group. So this is the same set that appeared in the previous talk. So adelic points orthogonal to the Brauer group. And we know that, yes?
You mentioned a name that is.
So the name is Shirashkin. I hope I've got that right. Yep. So this is his theorem, okay? This here. And another way of interpreting this set, which is sort of worked out perhaps a little bit later, is that this is also the finite abelian descent set. So this is a set of adelic points on the curve cut out by finite abelian descent. And I mean, I can be a little bit more explicit about what I mean by that in this context. You can embed the curve in its Jacobian, and then for any isogeny to the Jacobian, you can pull it back to get a torsor over C. And this set, by what I mean here, is the adelic points on the curve, which for any such torsor, that adelic point lifts to some twist. Okay, so that's the set that I want there. So this is something that's, I think, worked out quite explicitly by Stoll, but it's based on sort of earlier ideas in descent theory from Kolyotelen, Tsansuk, and Skorobogatov. But it's pretty well known at this point. Okay, so there's three ways of sort of interpreting this set, and all of them contain the set of rational points that we're after. So that was the first thing that Shirashkin did. But he went a little bit further, because this is a nice theoretical result. But for computational purposes, there's something else you can try, which is for adelic points. This is a product of points over the completions. My curve is proper, so everywhere that this curve has good reduction, I can reduce these. And so you get a map down into the product of the points over the residue fields. So these are the residue fields corresponding to the places V of K, and I'll just say V good, meaning V is of good reduction for C. So this is just reduce things where you have good reduction. And you could do the same thing for the Jacobian. And you get a commutative diagram like this. And then you can do the same, run the same argument. You're looking for these, so they're in the intersection of the images. And sort of being a little bit sloppy with the notation, I'll just write this as the product of the points over the residue fields in C intersected with the image of JK. And again, we're going to take the closure. Now, this is all happening here, and this is the product of the discrete topologies. So this is something that you can really hope to get your hands on. For example, what does it mean for this to be empty? It means that you can truncate this for some finite number of primes, and the intersection will already be empty. So you really can hope to compute this. And this is something that Shirashkin did in his thesis, and actually gave examples where he could compute this and consequently deduce there are no rational points on some curve. And well, you can see that that's actually due to the fact that there's a Brauer-Manin obstruction. Okay? So I want to put down a little bit of notation. So I'll borrow some notation actually from the previous talk. So we'll say that weak approximation with Brauer-Manin holds if what? I want that this set, whatever way you like to look at it, we know that it contains the rational points. I want to say that we have weak approximation with Brauer-Manin if the set of rational points on the curve is dense in that set. So if the closure of this is equal to this one here. Okay? And similarly, I'll just weak approximation with Brauer-Manin prime holds if this is true at the level down here in the residue fields. So holds if this is true So we'll write it this way. So the product of the points on the residue fields intersected with the closure of the image of the Mordet-Weil group, all happening down here. Okay? And so there's two more that I want to put in, which are the sort of analogs of this for the Hasse principle. So I'll call these HPBM and HPBM prime. And so what I want, so this is a slightly weaker property, which just says that if this set is empty, that whenever the set of rational points is empty, this set is empty, which is to say that the properties above hold whenever there are no rational points. So we'll say this holds if weak approximation holds whenever C of k is empty, and similarly here, but with a prime. Okay, so whenever this is true. All right, and so you have some obvious implications between these four properties. So certainly weak approximation with Brauer-Manin implies this Hasse principle, which is to say that the Brauer-Manin is the only obstruction to the Hasse principle. And you have this also at the level of the residue fields. Okay? And then what Sharashkin observed is that this set, when you reduce down this intersection that he's computing, maps into this. And so that immediately gives you this implication like this. And this is what he used to show, he computed the intersection there being empty. He used this to show that he's got curves with Brauer-Manin obstructions. Okay. Yes? It potentially, I'm just going to go with, for now, it could the way I've written it. Yeah. Now, the context that I'm going to move to is the case where it's constant curves, where the model I'm going to choose is the one over the finite field. So I'll just sweep that under the rug for now. Okay, so beyond these implications that I've written down, I don't think there are any obvious implications there. It may be true that all of these are true, in which case they'd all be equivalent, but this is sort of what you get from first principles. Okay, so let me give a little bit of the history here about these. So like I said, this was introduced by Sharashkin, and he made the observation that if the set of rational points on the Jacobian is finite, then, it's equal to its own closure, and so these sets actually cut out the set of rational points on the curve. So both of these properties hold in that case, and that's what he was using. But I think beyond that, maybe the first time this appears in the literature is a question of Skorobogatov, who explicitly asked if this Hasse principle, if the Brauer-Manin obstruction is the only obstruction to the Hasse principle, which would be this HPBM hold. So he asked this, and maybe I'll give myself some space here to continue. And so then after that, there came two conjectures a few years later. So one conjecture due to Poonen, and one conjecture due to Stoll. And so Poonen's conjecture was that you have that the Brauer-Manin obstruction is the only obstruction of the Hasse principle at the level of residue fields. So that was that the HPBM prime holds. And Stoll's conjecture was that weak approximation is satisfied at the level of adelic points. So these are the two conjectures. And maybe I should say that for the question and for these conjectures, they were originally stated over number fields. Yes, that's a good point. So I really mean to put a little bullet in the lower right-hand corner, which is I'm going to collapse the Archimedean place to its connected components. Thank you for that. Okay, so both of these conjectures would imply that Brauer-Manin is the only obstruction to the Hasse principle, but I don't think that it's clear that they're equivalent in any way. All right, so something about the motivation for these conjectures. So this conjecture of Poonen is based on a heuristic, which is if you look at the diagram up there, if you just imagine that or assume that the points on the curve over the residue fields are somehow random inside the Jacobian, and you assume that the Jacobian, the points on the residue field, the size of this you can estimate, and if you assume that this number, the size, is about as smooth as an integer of that size you would typically expect, then you work out the probability that you have a non-empty intersection, and it works out to be 0. So based on this, it seems if there's going to be something in that intersection, there has to be a reason. And one reason would be if you have a rational point, well, then it's, the images of the points on the curve are not random inside the Jacobian. So that's the motivation for this conjecture. And Stoll's conjecture, I think, is motivated by a lot of numerical evidence. So a lot of it's gathered by him and by others, have computed for many, examples, there are many more, but for lots of genus 2 curves have actually worked out the set of rational points using various techniques and sort of verified the conjecture. So it stands on pretty good ground. Okay, so that's all in the number field case. And I should mention the following theorem, which is due to Poonen and Voloch, which is in the function field case now. And it says that, in fact, this weak approximation with Brauer-Manin holds for I'll just say most, and I'll specify what that means in a minute, most non-isotrivial C over global function fields. Okay, so in the positive characteristic case, sort of prove the analog of Stoll's conjecture. So that's maybe even more evidence for the validity of this if you accept the analogy between number fields and function fields. So what is the most here? Well, so certainly the curve should be non-isotrivial, but one of the assumptions there is slightly stronger than that. And it's something that we've seen come up in some of the other talks about abelian varieties earlier in the week, is you really want something like the Jacobian has no isotrivial isogeny factors, or some kind of trace 0 condition or whatever. And there's another hypothesis that they have in the theorem, which is about the p divisible group associated to the Jacobian, where p is the characteristic of the field. But I've been led to believe that this condition could be lifted due to some recent work by Rossler. Okay, it may be possible. Okay. So it. Okay. So there we are. And one thing to note in this case is that it's not clear from the proof of this theorem. It's not clear if the result holds at the level of residue field, so this WABM prime, or even this slightly weaker HPBM prime. It's not clear if this holds. So the proof somehow uses information that's, I don't know, similar to what you're getting at the level of residue fields, at least somehow implicitly. But it also then does, on top of this, some very deep sort of p to the n descents for all n, which is information that I think just doesn't appear at the level of the residue field. So something deeper. So it's not clear what's happening in there. Okay, so then the question that I wanted to talk about today is what about constant curves? So, I mean, at the other extreme from this non-isotrivial, I mean, you could talk about isotrivial ones as well, but we'll focus on constant curves. And what do I mean by that? I mean that my curve C is actually the base change of some curve over a finite field, where here C naught is over the finite field, and K is the function field of some other curve over that field. Okay, so this is my question here. So these are not covered in this case, I mean, I guess typically you think that this is sort of the easy case when it comes to stuff over function fields, and it probably is easier, but somehow the hard case is already taken care of, so it's sort of reasonable to look at this. All right. So what we could say? So I want to mention one more theorem, and this is due to older work of myself and Bianca Virai and Felipe Voloch. In an earlier paper, we showed, what did we show? We showed that for these constant curves, that this Hasse principle with Brauer-Manin holds for constant curves provided the set of rational points on the Jacobian is not Zariski dense. So this is, I think, in some ways like a generalization of Shirashkin's result, that these things hold when the set of points is finite, but in the case of constant curves. And so then the theorem, or one of the theorems that I wanted to talk about today, which joint with Voloch, is that both the weak approximation with Brauer-Manin and weak approximation with Brauer-Manin prime hold for constant curves, constant C over the function field of D, and we have this condition when the genus of D is less than the genus of C. So again, some kind of condition we have to impose to get it. Okay. So maybe a remark or something to note here is in this case where we're talking about constant varieties over function fields, when we're talking about rational points, these have an interpretation. Well, they are literally morphisms from, well, the function field curve to C. So the set of rational points is in bijection with this. And in this situation, when we have this hypothesis that the genus of D is less than the genus of C, there aren't any interesting morphisms from D to C. We know that a priori. The only maps that you can get are the constant maps. Okay, so under this assumption about the genus. So in the context of this theorem, we don't really have any interesting rational points, and so the point of the theorem is not so much that we're pinning down the rational points because we already knew what those were, but it's that we can actually say that this is being pinned down by Brauer-Manin or by some finite abelian descent obstruction. Okay, so that's the result we have. Now we deduce this from some other results which I'd like to describe, which are really more about trying to characterize the set of points which on these constant curves which are orthogonal to the Brauer group. And well, my hope is that maybe those results will be of use in either proving a statement like this in more generality without some condition like this, or possibly if those properties don't hold, then they could be useful for finding counterexamples. So let me tell you about that. Can you say that again? No. Okay. So maybe I could have written that there. Yeah. So the question was, let me. Yeah. So the question was whether C of k is finite. Yeah. And maybe this is an important thing to note is that the second you have a non-constant map, it is actually infinite. So the naive sort of, I don't know, version of Falting's theorem doesn't hold. What is true is that there are only finitely many separable maps from D to C, but you have a Frobenius map from C to itself. So the minute you have a non-constant map you can compose with Frobenius, you get something of higher degree, and you can just keep doing this. So you are, in fact, infinite. Yeah. Which is also why, at least in this context, you really want to talk about closures, because these are not necessarily closed. It's an infinite set. All right, so in order to set the stage for the next theorem, I want to introduce a little bit more notation. So we all know what the adels are. So you have a product. So I'm in the context where my k is f of d, and my curve is a constant curve. So it's defined over f. So you have the product, a restricted product, actually, of the points in the completions with respect to the integer rings, right? So you're taking, for each place of k, points from here with the restriction that all but finitely many of them have to be integral. And what are the places of k? Well, they're now in bijection with the closed points on D, okay? And so this is your adel ring. These are your adels. And we have another object, which I'd like to introduce, which I call the reduced adels. And what is this? Well, it's a product again over the places of k, or the closed points of D, but now you're just looking at the residue fields. Okay? And one of the things that happens in the function field case is note that the residue field is actually contained in the completion. This is not something that you get over number fields. And what that means is that we can view this as a subset here, but in fact, it's a sub-F algebra of the adels. So we can view the adels. This is a K algebra, but K is an F algebra, so we can view this as an F algebra as well. So you get this sub-F algebra. Okay, and what that means, we can talk about reduced adelic points on our curve. A curve is defined over F. This is an F algebra, so we can talk about that. Right, so what is the adelic points? As you know, this is just the product of all of the points over the completions. And these reduced adelic points, this is exactly sort of the kind of sets that were appearing in Shirashkin's argument. It's the product of all of the points over the residue fields. Okay? And what the observation above is that we have an inclusion map like that. So this is some subset of the adelic points. And what's also true, because my curve is proper, so these points are all integral. And so you can actually reduce them mod v, and you get points down here. So you have here a kind of reduction map, which goes from these down to these reduced adelic points. All right? And now there's another nice way of interpreting these, which I'll write down. So what is such a thing? Well, it's for each point of D, you choose a point on C. So you can view this, if you like, as a map from the geometric points of D to the geometric points of C. And then the condition that the point in C you've chosen is over the residue field of the point here means that this map will be Galois equivariant. All right? So, I mean, when I say equals, I mean there's a sort of obvious bijection you get there. And I guess the bijection depends on choosing embeddings of the residue fields into an algebraic closure of F. Right? And then what's happening at the level of rational points? Well, you know that you can take rational points and stick them in the adelic points, and then you can apply this reduction map and you get points here. And this is actually an injective map. And like I noted up there, this is the set of morphisms from D to C. And there's an obvious map which says if I have a morphism from D to C, I just look at what it does to points, and you get a map like that. Okay, and this all commutes. So in this interpretation, rational points are morphisms between the curves, and adelic points are maps of sets between the curves. And so then the name of the game is to say, well, you know, what kind of conditions from finite descent or Brauer-Manin or something are going to pin down which maps of sets actually arise from honest morphisms. Okay, so here's the theorem, which, well, it does a couple things, but in one part it sort of gives an interpretation or characterization of this finite abelian descent obstruction in terms of these maps, which is somewhat interesting. So this is, again, joint with Voloch. So I'll state this with 3 parts. So the first part is that, so this is for constant C over f of D. No assumption on the genus or anything like that at this stage. So the first statement is that the weak approximation with Brauer-Manin is actually equivalent to the weak approximation with Brauer-Manin at the level of these reduced adelic points. Okay, so these 2 notions are the same, which is kind of what you would hope because everything is defined over the finite field. So you should be able to, smash it down here and see what's going on. So statement 2 is that if you look at the set relevant to this property, right, which was, so before it was the product of the points on C over the residue fields, but now I'm calling it the reduced adelic points of C, and if you intersect this with the image of the Mordé-Weber group and the closure of that, so this is taking place in the set of reduced adelic points of J, but this is the set relevant to this property here. This is equal to the set of reduced adelic points on C, which are orthogonal to Brauer. Or you can also describe it in terms of descent as the set of points which survive finite abelian and etale descent. So before, at the level of adelic points, the Brauer set corresponds to the finite abelian descent set, but you definitely have to allow for non-etale coverings, say, so these p to the n coverings that were used in the proof of the theorem in Voloch, for example. So there's a slight sort of improvement here. You can restrict to torsors under etale group schemes, and even to torsors over C over the finite field F. All right. And now the third statement is the one that sort of gives the characterization that I was alluding to. So let's suppose you have oh no, so okay, so for the finite abelian descent, I'm saying you take any isogeny to the Jacobian and you pull that back. So you're allowing for non-etale. Yeah.
Abelian does not mean Galois.
Yeah, it means a torsor under finite flat abelian group scheme, something like this. And I guess the ones that I was using were all geometrically connected as well. But so this is you're taking isogenies to the Jacobian that are etale. Okay, so suppose we have an element in here, so one of these reduced adelic points, and we know that this corresponds to some map between the set of geometric points on F and the set of geometric points on C. Okay, and then the statement of 3 is that this point survives Brauer if and only if a property about this map. So this map between points obviously induces for you a homomorphism between the groups of divisors, just by, if you extend it by linearity. And the claim is that that induced map sends principal divisors to principal divisors, which means that it induces a homomorphism between the Jacobians. So if and only if phi induces, and it's a homomorphism that's GF equivariant, so a GF module morphism. So you have the geometric points on the Jacobian of D mapping to the geometric points on the Jacobian of C. Okay? So it's kind of an interesting condition that this induced map gives you that, and it's if and only if. Okay, so here's a question, which is really a reformulation of the question of whether this property holds, but I'll phrase it in terms of this language, is suppose you have a GF module morphism like this. Okay, and you have the property that you have the Jacobian, you have the curves embedded in here in such a way that if you, well, maybe we call this phi, such that if you map the points on D over, you end up on C. Okay? So you have a map between Jacobians, or the points on the Jacobians, which sends one curve to the other curve. The question is, does that arise from an honest morphism from D to C? Yeah, so I mean a GF module morphism. So it's a homomorphism which respects Galois. Excuse me? Can you use Tate conjecture? So our proof, well, no, I don't know actually. Yeah.
Tate conjecture tells us that if you have but it's a morphism, right? No, it doesn't say anything about curves. Because here you won't have some curves, all have some.
Well, I guess it means that it can be approximated by such a thing. Not necessarily that it's a morphism. So with regard to this question, there is one result anyway, which is due to Zilber, and is based on some model theoretic techniques. The claim is that the answer is yes, provided this map that I called phi is an isomorphism. So that gives at least one other case where this weak approximation with Brauer-Manin holds. It's not a condition that's very easy to verify whether if you have a reduced adelic point on the curve and you look at the induced homomorphism between the Jacobians, and if it's an isomorphism, then it comes from a rational point. But that's what it says. Okay, well, let me say a few words about the proof. Not of Zilber, but of the theorem there. So you got the three statements. So the first statement is about the equivalence between these two at the level of adelic points and at the level of these reduced adelic points. And really the idea there is to do Fn descent, where F is the Frobenius on the curve. So you do descent with respect to this, and well, that's maybe all I will say about that for now. But for 2 and 3, maybe I'll give a little bit more detail. But the main idea for these is to do 1 minus Fn descent. Okay, and I mean this for all n. So what is 1 minus Fn? This is an isogeny, an endomorphism of the Jacobian. And what is its kernel? Its kernel consists of all the points which are defined over some field of degree dividing n. Right? So it's points that are fixed by Fn are going to be killed by 1 minus Fn. And if you like, you could take this to be, say, n factorial or something, and then you can think of the kernel as consisting of all the points on the Jacobian, which are defined over some field of small degree. All right? And so how do you use this in that context? Well, what does it mean for an adelic point, a reduced adelic point on the curve to survive this? Okay? It means you work it out that for at all the points of small degree, the map that corresponds to this reduced adelic point at those points of low degree looks like what a morphism would do to those points of low degree. So you're basically finding that the map corresponding to the adelic point agrees with some honest morphism on an arbitrary finite subset of D, and that's basically what it means for that adelic point to lie in the closure of the Mordé-Wehr group. Okay, so that's maybe a lot to take on, but if you want more details, you can ask about it later. Yeah?
So in the question and in Zilber's statement, I mean, if you take D equals C,
Yep.
and then if you take for any power of the Frobenius morphism,
Yep.
then that'll give you.
So the Frobenius gives you an isomorphism of groups.
Yeah, and that comes from morphism because it's an integral power.
Yeah.
Couldn't you take a Z hat power of Frobenius?
So it's
And then it would still be an
yeah, I guess that's what we want it to be. That would put it in the closure of the set of rational points on the curve, and that would be sort of okay. So maybe I should modify the question to.
So
could it be a limit of?
I guess Zilber must have to deal with that.
I mean, I think he says up to Frobenius twist or something, which just means it means I've.
Z hat
Yeah,
powers of Frobenius.
I suppose. Yeah. Anyway, so the moral here was that points that would survive this lie in the closure of the Mordé-Wehr group. You just work that out, and that's sort of the basis of certainly for 2, and for one direction of 3, and for the other direction of 3, which is that if you have a homomorphism between the Jacobians with those properties, that it gives you an adelic point. This is based on Tate's theorem, Tate's isogeny theorem, or Tate conjecture, I guess, which is theorem there. And the point being that if you have a homomorphism between the points on the Jacobians, this gives you a morphism between Tate modules, and then you can approximate that by the theorem. Okay, so maybe I will try and tell you how this theorem implies the statement I made about the theorem with the restriction on the genus. So I didn't number these, but if that's theorem 2, how does that imply theorem 1? That's what I'd like to give you the idea behind. So what we're doing, we have an adelic point on my a reduced adelic point on this curve, which survives Brauer, okay? And by the theorem, we have the corresponding map between Jacobians with phi of D contained in phi of C. And we'd like to prove, so we have also a hypothesis on the genus, but under that we'd like to prove that this adelic point is actually a global point. And now the hypothesis on the genus, remember, told us that, so we had G of D is less than G of C. So this tells us that the only global points are over the finite field. So what we want to show, or what we must show, is that phi is 0, the zero map. Okay, so it has to be a constant map, and it's homomorphism, so it's got to be 0. So how do we do this? Well, you've got the points on the Jacobian, and you can write these as points on the image of the g-dth symmetric power of D. Right? So you take the g-dth symmetric power and its image in the Jacobian, and we know that this is equal to that because GD is the genus. Okay, and so now you can apply your map, and this is still true. And this now, if you think about the way that homomorphism between the Jacobians is defined, you just have a map between points and you extend by linearity to divisors. This is going to end up being contained in the image of the g-dth symmetric power of C in its Jacobian. And the point is that because GD is less than GC, this is definitely not equal to the entire Jacobian. So your assumption on the genus is forcing this map between the Jacobians to not be surjective. Okay? And then what do you do? Well, if you take Zariski closures of everything, over here you get the whole Jacobian, and over here you get, well, this is a subgroup of the set of points, and you take the Zariski closure, there's some proper algebraic subgroup containing that. Okay? And then the idea is, well, C intersect G is finite. Okay, here I guess I have to assume that, well, yeah, that's fine. C intersect G is finite. And so that means that this map between the curves has a finite image, and this actually implies that the map between the Jacobians is also finite. And that's because, I mean, how the map is defined, you've got finitely many points on C. The image is contained in the group generated by those finitely many points. But because we're over a finite field, all of those points are torsion. So the minute this image of C is finite, this is going to be finite as well. Okay, so now you have this finite group, but it's the image of a divisible group. So it's also divisible. And there's no finite divisible groups other than the trivial group, hence trivial. Okay, so that's how you deduce one theorem from the other. And I would say that so there's the theorem that I mentioned before, which was joint with Bianca, and it has a similar flavor in that the hypothesis was that the rational points on the Jacobian are not Zariski dense. In the same way, that means sort of images are contained in some proper algebraic subgroup or translates of these things. So you get sort of a similar result that way. Okay, so I've got a little bit of time left. And so I'd like to talk, so all of that was sort of about finite abelian descent in a way. And we also have a rather nice characterization, I think, of finite etale descent, which is not necessarily abelian. And there's a connection to this with so-called anabelian geometry. So I want to maybe spend just a couple minutes motivating this in the number field case. So all of this is about, and this is something that could have come up in Jordan's talk. So now I'm talking about C over K, K global field, not necessarily a constant curve anymore. Okay? So you have the etale fundamental group, and it sits in this exact sequence. You've got pi 1 of spec K, which is the absolute Galois group. And I guess the philosophy of anabelian geometry, I don't consider myself an expert in this, but is that for some appropriate category of anabelian varieties, you should be able to reconstruct the variety from its fundamental group, or perhaps from this exact sequence. And more than that, should be in a kind of categorical way that morphisms between fundamental groups, or these sequences, should correspond to morphisms between the varieties. And the example that was mentioned in Jordan's talk was about the section conjecture, which is that if you have a section of this, that would predict, perhaps, that you have at least in the number field case, predict that you have a map, a morphism from spec K to C, so you should get a rational point. Okay? But so what's certainly true is that if you have a rational point, by functoriality, this gives you a section like that, and I'll write this. This is notation that I've borrowed from Jakob Stix. So this is the set of sections. So this is sections of star up to pi 1 C bar conjugacy. So the conjugacy comes in, you've picked, I haven't written it in the notation, but supposing you pick a base point of C bar that's compatible with the base points here, why this happens is that the rational point that you have may not be landing right at the base point, and so in order to sort of compute the induced map, you have to choose a path from the rational point to the base point, and there's some choice depending on the geometric fundamental group there, which is what you get there. Okay, so you certainly have this map, and it's known to be injective, and the section conjecture of Faltings is that it's actually an equality. And there's a connection with this to descent, which is well known, which is, so now I'm going to talk about the number field case, I guess, these statements that I made here about the number field case, is that you certainly have this, and there's another object over here, which are the adelic sections. Okay, what is an adelic section? It means for each completion you can base change the sequence. You have a section of that sequence up to conjugacy, and then some condition that they're almost everywhere unramified. Okay, but you certainly have maps like this, and what's the connection here is that if you look at those adelic points which survive finite etale descent. So now I'm talking about torsors under all finite etale group schemes. There's a similar notion that you can apply here. And what's the theorem is that this map this way is actually surjective. And so this is due to Stoll, Harari, Stix, and maybe a little bit of an extension by Stix himself. And the surjectivity of this map, what it tells you is that in fact the section conjecture implies that this is the set of rational points. Okay, so the section conjecture implies that this set, so the fact that this is surjective, this map is known to be injective. If this is an equality, all of these arrows are equalities. So you get that. Okay? So that's something that could have appeared in Jordan's talk, I guess. I don't know. So we have, the last thing that I'll say, we have a result which is kind of an analog of this, which I'll try and describe. So now I want to consider C and D over F, and K is equal to F of D, as before, so constant curves. And what we have, the set of rational points, as we've seen, this is the same as morphisms between D and C. And just like in that case, a morphism between the curves will induce a morphism between the fundamental groups. So you get a map to homomorphisms between pi1 of D and pi1 of C. And then again, there's some issue up to conjugacy. So I will say a little sub pi1 of C bar there is to say that this group of homomorphisms modded out by composing with conjugation by an element coming from the geometric fundamental group of C. So that's just functoriality gives you that. Now this set is something like the analog of the set of sections here. But unlike the number field case, it's actually not surjective, this map. What you can say is that there's certain conditions that these morphisms, the images of morphisms satisfy. So there's one condition which I call locally Diophantine, which means that the decomposition groups in this fundamental group are mapped to open subgroups of decomposition groups here. And this is something that's automatically true for morphisms coming from morphisms of the curves, but you can write down examples that don't have that property. All right? And now we have a map to our reduced adelic points. And we can look at those reduced adelic points which survive finite etale descent. That's sort of the analog here, but now with the reduced adelic points. And our theorem is that there's a map like this, which is a bijection. Okay, so it's in some ways a little bit stronger than the analog here, which would be that there's some, local versions of this, which is in bijection with that. We actually get a bijection between this and the sort of global object. So I guess I only have a couple minutes left, and I'll try and say maybe just very briefly what the idea is. It's quite similar to what's used here, and namely, if you have a point which survives finite etale descent, so you've got your adelic point which survives that, that means whenever you write down a torsor over C under some finite etale group scheme G, you can find a twist to which this lifts. Okay, so this gives you some, some cohomology class in H1 of KG, and what you can show is that this actually has to be unramified, which means it's actually a class in H1DG, which means you can actually interpret this as this class that you have to twist by. You can interpret this as a torsor over D under the same G. And once you have this, basically, you've got a functor, which is sending etale coverings of C to etale coverings of D. And that gives you, sort of because the fundamental groups are classifying these things, that gives you a morphism from the fundamental group of D to the fundamental group of C. So similar ideas at play here. There are a few differences, but I think maybe that's a good place for me to stop.
Any question? Wait for the...
So the proof of this statement here is quite different from the proof where you use Zilber's theorem.
I didn't use Zilber's theorem.
It
was just an observation that he has a result.
Okay, so
Yeah.
you can do with that. So in fact, the two proofs are sort of related. I mean,
I mean, there is a sense in that, like in the abelian case, we're looking at homomorphisms between the Jacobians, which are sort of homomorphisms between the Tate modules. So it's like the abelianized version of the fundamental group.
Yeah,
so there is a similarity, in my sense. I mean, we have kind of two different ways of proving it, but the results are somewhat analogous.
Okay, thank you.
Other questions?
For the second theorem, did you say that's under the same assumptions as your first theorem, or is this for any
This is
curves?
for any constant curves.
Okay, so
over
no
global function
no
fields.
relation
No-
on the genus.
No.
More questions?
In the last statement, when you have homomorphism from pi1 of D to pi1 of C, this is really a homomorphism of the fundamental groups defined over the base field. I mean, because when you twist, you can go from Galois etale covering to a torsor under some finite group scheme.
Yeah. So here, I'm actually restricting to torsors under group schemes over F. So I never leave that world.
Ah, okay.
Yeah.
So
Yeah.
it's really a morphism between the fundamental groups themselves. Okay, thank you.
More questions? If not, let's thanks Brendan again.